Good morning. First of all, thank you very much, Yves, to give me the opportunity to talk about my preferred gap in space. I will present you a research on which we're working now for about 4 years on electromagnetic absorption. I'm not at all from the electromagnetic field. I've learned a little bit about it for the last few years, so I'm not on a very stable ground for me. And as soon as possible, I will jump to mechanical aspect, you will see. But so I will start by acknowledging the collaborators. A major part of the work has been carried out by Pierre Bollen, who is a PhD student now in his last year of his thesis. And Nicolas Kévy was a postdoc. Isabelle Oynen, she is the one who knows everything about electromagnetism. Christian Bailly is a polymer specialist. Christophe de Trembleur and Jean-Michel Thomasin are chemists. So it's a group of a variety of expertise. Before I introduce you to my preferred gap, I will explain you the general ideas of what we have tried to accomplish for the last few years. There are two ways to protect an object or human people or anything else to EMI, to electromagnetic interference, or to protect and to shield an object. The first one is the one you know the best, is just protect the material by a reflective layer such that all the incoming electromagnetic power is just reflected. And this would typically be the Faraday cage approach, where you use a metal and you just reflect everything. The other approach, and I will explain you why it is sometimes interesting, is to absorb the electromagnetic radiation. So to let the wave enter the material and just dissipate the energy into the material. But 99% of applications are based on reflection. Now, why is it sometimes useful to absorb and not to reflect the electromagnetic radiation? First example is in microelectronic or power electronics application. The fact that you will put a sort of shield around the devices would lead to reflection inside the system. So for most applications, it's absolutely forbidden to have waves getting out of the system, so you will reflect, but you might have interferences from one device to another inside a chip. And so that means that the fabricant of these systems, they have to put barriers in between all the chips, and still like that they sometimes face some trouble. So it would be better to have in some application an absorbing material and avoid these bad reflections. Sometimes also you can have problems like in windmills. For instance, it's known that windmills affect the radar operation. That's why you cannot put a windmill within a radius of 15 kilometers around airport. So around every airport, you have to draw a circle of 15 kilometers radius. And you cannot put a windmill, and this is because of the interference. So it would be a good idea to absorb the radiation and not to reflect it on windmills. People working with electromagnetic devices and testing many different systems, they use anechoic chambers, and these chambers are designed with these very strange walls. You might have seen that before, such that the waves are absorbed and not reflected in order to allow calibrating devices and so on. And of course, you know that there are claims that electromagnetic radiation might affect living cells. My colleague Isabelle Oynen is in one of the team in Europe who has been working a lot on this topic for many, many years, and they have mixed claims. So they have seen some evidences of disease in rats and so on, but it's not so obvious. But there might be, and I will not enter one of the favorite topic of Yves, of the principe de précaution today. Otherwise, this talk can last for hours probably. So, but there might be some aspect there. Okay, I will start by showing you how we derive a material index, which quantify the quality of absorption And then from there, we will see if a material exists. And the answer, you know, will be no, to optimize this index. Okay, I will not enter the details of the analysis, but basically you have to use a line transmission formalism. You have an input signal, and this signal will transmit and reflect through the material, and you just have to set up the boundary condition to make the field, the electrical and magnetic field, equal at the entrance and the outside surface of the material. I'm not entering in the detail because you probably don't want to hear that. But at the end, what we calculate is the absorbed power. The absorbed power is the input power minus the reflective power minus the transmitted power. So it is really the power that is dissipated into the material here. And we define the absorption index, and that will be the performance index of the problem. It is the absorbed power divided by the input power, meaning that 1 would mean that there is no power that is reflected and no power transmitted. So the goal is to be as close as possible to 1. And at the end, if you work out the equations, and this is all analytical, you're getting a messy performance index, but still it is analytical. And you see that this absorption index depends on the reflection and the transmission. And the reflection and the transmission, they are both connected to the effective dielectric constant of the medium. And at the end, the effective dielectric constant is a function only of the dielectric constant and the conductivity of the material. So this is a function of dielectric constant and electrical conductivity. Plus, unfortunately, you cannot decouple this performance index from the frequency and from the thickness of the medium. So the thickness enters the transmission here, little t is the thickness. So there are two system parameters entering the performance index. It's not possible here to extract only the material properties. Okay, let's see what this performance index tells us. So we have to fix the frequency. So let's take 10 gigahertz, and let's fix the thickness of the material. Okay? And then for these two numbers, let's calculate what is the value of the performance index in the dielectric constant electrical conductivity space. And these are isocontour or performance index, and when it's red, it's closer, it's the closest to 1. And what you see is that there is a very clear, very narrow region where you can reach high energy absorption. And it's around 1 Siemens per meter, and it's for the lowest possible dielectric constant of 1. This is where you want to go. Now, if you change the thickness, you will just change the magnitude of the absorption. So if you increase the thickness, you will just get more red here. And if you change the frequency, you're going to shift left or right the optimum conductivity, but not that much, just by a decade or two, not more than that if you change many decades in the frequency range. This is a plot where you see for a given frequency what is the optimum conductivity depending on the frequency, and what is the thickness that gives you the absorption index you want to reach. So if you want to reach 90% of absorption, and say you have a material that has a dielectric constant, a permittivity close to 1, if you want to reach that, you need a thickness of here 50 millimeters, and you need a conductivity of something like 8, 10 to the minus 1, something like 0.2 Siemens per meter. Okay, so depending on the frequency, the optimum conductivity will change. Okay, let's see how we can select a good material for that. We use EduPack here, and we plot all materials, dielectric constant as a function of electrical conductivity, and this is the area where we look for an optimum value. I've made a more simple schematic plot here, and you see the different families of materials, and you see the range of optimum absorption here. And this is the gap, where you see there are no materials here There are a few materials that are not too far, but the fact that the region in which you can get high absorption is so narrow that all the materials around basically have zero absorption capacity. So you really need to have a very good control of the electrical conductivity here to reach this area. The closest is leather, which in terms of absorption would be the closest to here. I've not drawn it, but so natural material are the closest, and silicon carbide foams should be the closest. Okay, so our strategy was the following. In order to fill this space. This is the way I reinterpret what we have done. Of course, we have not followed that logic. It's now easy to present it this way. We started with polymers, which have a low dielectric constant, and added the right amount of carbon nanotubes in order to increase the conductivity in the range of a Siemens per meter, which means about 1% or less of carbon nanotubes, so not a lot. And you need to control this very well. Unfortunately, when you increase the conductivity by introducing carbon nanotubes, you're getting a higher dielectric constant. So in order to reduce the dielectric constant, the idea was to foam this nanocomposite. So mix of polymer nanotubes, then foam it, and by just a law of mixture, you're reducing the dielectric constant. Not to 1, unfortunately, but 2 or 3, depending on the material. I have examples here where you have in black here a solid material with on carbon nanotube, so not the right conductivity, and then you make a foam. You see that the dielectric constant is decreasing in the entire frequency range. Here it's in gigahertz, and you see now for the solid material with carbon nanotube and the drop when you foam it in terms of dielectric constant. Okay, but like I said, it was okay. We could get relatively good absorption, but the question was, can we do better? And the idea was to mix this foam with aluminum honeycomb. Initially, the idea was only for mechanical purpose. I thought that by putting this foam inside the honeycomb, we could improve the mechanical properties while not changing the electromagnetic properties. And the good news is the following, is by introducing the foam inside the aluminum honeycomb, we also got an improved electromagnetic absorption. So this was the absorption just of the foam with the nanotubes, and this was the result of the absorption as a function of the frequency for the foam inside the aluminum honeycomb. So very good news, because we got a synergy effect. And my colleague Isabelle Leinen and myself, we worked on trying to set up a model to explain why we are getting this improved electromagnetic efficiency. And the reason comes from a waveguide effect. The aluminum honeycomb is playing the role of a waveguide, and by this effect, is sort of reducing the dielectric constant of the medium. I will not enter into the details, but once again, we can get a closed form expression for now the new effective dielectric constant of the medium, and so the material is not a complicated material, it's a foam with carbon nanotubes inside a honeycomb, okay? It's all analytical, and the result is the following. If now we express the contour plot again in the same space, with the honeycomb compared to without the honeycomb, you see that the optimum dielectric constant, effective dielectric constant of the medium, owing to the aluminum honeycomb, is moving up to values between 2 and 5. While earlier we had to reach 1, which we can't, of course. We would need open space to do that. So now it's possible to reach the optimum point owing to the presence of the aluminum honeycomb. So we prepared several samples, and Pierre prepared several samples of aluminum honeycomb filled with the foam. And you see the experimental results are, of course, the result with the scatter, and it has to do with the way the experiments are performed. It's not because Pierre is not agile enough. The model, when it's written model, it means the analytical model, and we confirm the validity of the analytical model using finite element simulation. The good news is the analytical model, of course, can be used for optimization, which is more difficult with FE simulation. And you see here, very good absorption for this size of honeycomb in a range here of above 3 or 4 gigahertz. Below 3 or 4 gigahertz, depending on the size of the honeycomb, you have the cutoff frequency, and there is no effect anymore of the honeycomb, and basically then waves are transmitted. So these are other examples where it's a combination of analytical modeling and finite element models for the absorption here for a 2 millimeter honeycomb and for a 0.9 millimeter honeycomb size. And you see that larger is the honeycomb, larger can be the wavelength, smaller can be the frequency at which you can have absorption. So basically, this is the cutoff frequency. We can only absorb above 2 gigahertz for this size of honeycomb. Okay, how do we make this material? It's not that difficult. We have 2 different approaches to do that. You can either make the foam inside the honeycomb, or make the foam and then insert mechanically the foam inside the honeycomb later on. In order to form directly the material inside the honeycomb, we use either supercritical CO2 approach, and these are the colleagues of the University of Liège who have developed this method. This gives the best foam, but it's more complicated, of course, to make this, to play with this technique. Or we can use chemical foaming, but then it's, of course, give rise to a foam with larger pores, and the mechanical properties of the foam are a bit worse. The other approach is mechanical insertion. We make the foam, and then we press the foam inside the honeycomb. Our preferred method up to now is chemical foaming. And these are examples of material samples that have been produced. And right now, what Pierre is able to do is a square like 20 centimeters by 20 centimeters, which looks like this, so much, much wider. So different sizes, different thicknesses to play around. All right, so this is the multi-scale structure of the foam. And I will say now just a few words about the other properties, of course. Electromagnetic absorption is okay, but we need to reach other performances in order to make this material useful in different applications. So in order to meet some mechanical requirements, for instance, for aeronautic applications, we introduce this hybrid material as the core of a sandwich. So this is the core material, and we use glass fiber reinforced polymers as phase sheets, not carbon fibers or no metals, otherwise we just lose the entire absorption capacity of the material. We would reflect, again, the incoming power. So we use glass fiber material. The good news is that with the glass fiber composite on top of the material, we're not losing the EMI, the electromagnetic shielding capacity or absorption capacity. We even improve it a little bit. So black is for just the core, and red is for the core plus the phase sheet. This is the absorption index as a function of frequency again. Now the question is, do we get good mechanical properties with this material? And then we have been lucky to see that the presence of the foam inside the aluminum honeycomb is playing a very interesting role in distributing the load and constraining the face of the aluminum honeycomb. And instead, during compression of having a single buckling mode, we're getting a multiple buckling mode under compression. So there is much more mechanical energy that is dissipated during the compression of this honeycomb when there is a foam inside. And these are the compression curves for the honeycomb, just the foam, and the synergy of the two. We have performed bending tests on different sizes of honeycombs and different thicknesses in order to evaluate what's the bending modulus, as well as to detect what are the failure modes. And the failure modes are indicated here. Depending on the orientation of the honeycomb with respect to the bending, we're getting either decohesion between the foam and the face of the honeycomb, and then finally decohesion of the face sheet, or sometimes we can have decohesion in between the layers of the honeycomb. Now, one good point that we realized in a few months ago, is the fact that owing to the foam inside the honeycomb, it's much easier to bond the phase sheet compared to the classical strategy where you have to bond a phase sheet on a honeycomb. And this makes the bonding, the adhesive bonding, more complicated because you're just bonding on a small edge. While when you have the foam all inside, you have a full surface to improve the adhesion. We have made some impact tests. This is just the honeycomb, and this is the honeycomb filled with the foam, and the way the load is distributed and is much better in terms of energy absorption. It's better also, and we avoid, for the range of parameters we have tested, we avoid complete penetration owing to the presence of the foam. This is for mechanical properties, and there are some reports in the literature explaining how to optimize a foam-filled honeycomb, and perhaps you will not save mass, but you might save in terms of the thickness at the end. So for application in which you want to decrease the thickness of the sandwich, it's interesting. Now, in terms of conductivity, I don't know what's the time. Because okay, just a few words about the conductivity. Of course, the conductivity, we have played with many different polymers: polyurethane, polycaprolactone, polycarbonate, but of course we have here an insulating material. The conductivity coming from the carbon nanotubes is the additional conductivity is extremely small. Even though we have electrical percolation, the way heat is transported in the carbon nanotube networks is very poor. So basically, it's an insulating material. The only heat that it transported really is through the face of the aluminum honeycomb. But of course, you could play around and even improve the insulation by replacing the aluminum honeycomb by a Nomex honeycomb and metallize the surface of the Nomex, which would give the insulation of the Nomex material, or polymer-based honeycomb, and still have this waveguide effect by metallizing the surface. So we really played the game of looking at some optimization, and for different kind of constraints, different objectives, different variables. So this is just one example to show you that you can push the strategy using the approach of Mike HB until the end. If you look at a material which absorbs electromagnetic power and has optimal thermal dissipation, you can set a value of absorption, 90%, 95%, as a constraint, and then, for instance, maximize heat flux, or minimize. Maximize would be for a thermally conductive material, which is not the best for our material. And the performance index then becomes a thermal conductivity divided by the thickness, and the thickness hides, as a matter of fact, the thickness is hiding the absorption capacity. So you go for every material, you look at the dielectric constant and electrical conductivity, and in order to reach an absorption of 0.9, you will get a value of the thickness. As a matter of fact, for most material, the thickness will be infinite because they have no absorption capacity. There is a narrow set of material for which you will have a value of the thickness, and then this is a comparison of the performance index for different materials, the leather, silicon carbide foams, and so on, compared to our hybrid materials. And the material is doing a fairly good job to optimize the performance index, even if it's not the best application here, because it's more thermally insulating than thermally conductive. Okay, as a conclusion, this is the hybrid architecture that I have presented to filling this gap in the dielectric constant electrical conductivity space, where you have a sandwich. The core of the sandwich is a honeycomb, and the honeycomb is made of a foam, and the foam itself is a polymer reinforced with carbon nanotubes. You have seen that the range of frequency in which where we can absorb is above a few gigahertz. This is fine for many applications. Cellular phones, radar, many radar operate in the range above 2 gigahertz. There are some applications where it would be nice to absorb below, and we're working now, and Pierre is working, and this is the end of his thesis, to a metamaterial approach where we develop a concept where you can have a dielectric constant below 1 and permeability which is below 1. I think my time is reached, so I'm just showing you this image of what Pierre has recently performed. On top of all the material here, is also introducing some thin copper rings inside the honeycomb, and there will be the foam around. And this ring is adding an extra capacity into the system and transform the material into a metamaterial. And by doing that, he is able to get absorption peak below the cutoff frequency that we have. So it's not as good as what we have above 2 gigahertz, but it opens some avenues to also absorb below the 2-3 gigahertz range. So based on that, I thank you for your attention. No.